All right, today we're pulling back the curtain on some seriously cool hidden physics. I'm talking about the science that governs pretty much everything that flows, from the clouds way up in the sky to the blood pumping through your veins. It's literally all around us, always in motion, so let's get right into it.
So, let me ask you a question. It kind of sounds like a riddle, doesn't it? What could a rushing river, the air you're breathing right now, and the fuel in a rocket possibly have in common? I mean, they seem like they're from completely different worlds, but believe it or not, they all share one fundamental, really powerful identity.
And there it is. The simple answer is they're all fluids. And because they're all fluids, that means they all play by the same elegant set of physical rules. And you know what? Understanding those rules is exactly what we're going to do right now.
Okay, so first things first, we need a solid definition. What exactly is a fluid? You might be surprised to learn that it has less to do with what it looks like and everything to do with how it acts when you push on it.
This right here shows the core difference perfectly. Think about it. If you push along the top of a solid, say a block of wood, it's going to push back. It holds its shape. That sideways pushing force, well, that's what physicists call shear stress. But now imagine trying to do the same thing to water. What happens? Your hand just glides right through it. Fluids don't really resist that force. Instead, they flow.
And that brings us to the official definition. A fluid is basically any substance that just keeps deforming or flowing as long as you apply that shear stress. And what's so cool about this simple idea is that it connects the obvious stuff, like water and oil, to the things we can't even see, like the air we're breathing or the steam rising from a kettle.
So, we know what a fluid is, but how do we actually talk about it? How do we describe it? Well, to do that, we need to learn its language, the key properties that let scientists and engineers measure, compare, and even predict what a fluid is going to do next.
First up is a big one you've probably heard of: density. All it is, really, is a measure of how much stuff, or mass, is crammed into a certain amount of space. We use the Greek letter rho to represent it, and the formula couldn't be simpler. It's just mass divided by volume. That's it.
To make this a little more real, let's use a benchmark that everyone knows: water. Picture a cube that's 1 meter on every side. If you filled that cube with water, it would have a mass of 1,000 kilograms. So its density is 1,000 kilograms per cubic meter. And trust me, that number is basically the foundation for almost everything else we're going to talk about.
All right, now there's something closely related called specific weight. We use the Greek letter gamma for this one. And here's the key difference. While density is about mass per volume, specific weight is all about weights per volume. And since weight is just mass with gravity pulling on it, the math is super easy. You just take the density and multiply it by g, the acceleration due to gravity.
Okay, but what if we want to make comparing densities even easier? Well, for that, we have something called specific gravity. This is a super clever shortcut. It's just a simple ratio that compares a fluid's density to our benchmark, the density of water. If the specific gravity is less than 1, it's lighter than water, so it'll float. If it's more than 1, it's heavier, and it'll sink. It's an incredibly handy tool. Let's look at some real-world examples here. So water, our benchmark, has a specific gravity of exactly 1.0. Makes sense, right? Now look at gasoline. Its SG is 0.68. Right away, you know it's way less dense than water. Jet fuel is a little bit denser at 0.804, but still, it's going to float. See how useful that is? This one little number, with no units, gives you an instant feel for the fluid. All right, let's switch gears and talk about another key property. What happens when you try to squeeze a fluid? You know, some things, like gases, are super easy to squash down, but others, like liquids, they barely budge. That resistance to being squeezed, that's what we call compressibility.
So, the sciencey term for this resistance is the bulk modulus. We use the letter E for it. And the rule of thumb is really simple. The bigger the bulk modulus, the more incompressible the fluid is. It just means it fights back harder when you try to squeeze it. And whoa, check out this chart. It shows just how huge the difference can be. Just look at that. Water's bulk modulus is more than 15,000 times bigger than air's. That's why you can easily pump air into a bike tire, but trying to squeeze the water in a sealed bottle? Yeah, good luck. It's practically impossible. The difference is just massive. And to put a hard number on that, get this. If you increase the pressure on water by 1 whole atmosphere, we're talking the entire weight of the air column above us pushing down, the water shrinks by only 0.005%. That's basically nothing. It's so tiny that for most real-world engineering, we just treat liquids as if they're completely incompressible.
Okay, so we've got our definitions, we've got our ways to measure things. Now we get to the really powerful stuff, the 3 golden rules that govern how every single fluid in the universe behaves.
It all boils down to these 3 core ideas, what's known as the conservation framework. In any system, whether it's a fluid or not, mass, momentum, and energy are always conserved. You can't make them from scratch, and you can't destroy them. They can only be moved around or changed from one form to another. These are the absolute golden rules of physics. First up, conservation of mass. This one's pretty intuitive, right? You can't just create stuff out of nothing. For a fluid, it just means that whatever flows into a pipe, for example, has to either flow out the other end or build up inside. The books always have to balance. Next up, conservation of momentum. The easiest way to think about this is like Newton's famous second law, F equals ma, but for fluids. Basically, if you want to change how a fluid is moving, speed it up, slow it down, change its direction, you've got to apply a force. This is the very principle that lets a sailboat catch the wind, and on a much bigger scale, it's how a rocket works, by throwing mass out the back to push itself forward. And last but not least, the conservation of energy. You probably know this as the first law of thermodynamics. Energy in a fluid can absolutely change its form. Like the energy that's stored as pressure can turn into the energy of motion. But the grand total amount of energy in a sealed-off system never ever changes. It's all got to be accounted for somewhere.
All right, we've covered the definitions, the properties, and the 3 golden rules. So now it's time to put it all together. Let's apply these tools to a real-world problem and see how they work.
So here's our scenario. We've got a tank of oil, we know its volume, and we know its mass. The question is, with just those 2 numbers and the formulas we just learned, what can we figure out? Turns out we can figure out a whole lot.
Let's just walk through the math here. First, we get the density. We just divide the mass by the volume, and that gets us 900 kilograms per cubic meter. Simple enough. Next, we want its specific weight, how heavy a chunk of it is. So we just multiply that density by gravity. And then, for that quick and dirty comparison, we calculate the specific gravity. We divide our oil's density by water's density, and we get 0.9. Boom. That one number tells us everything. This oil is 10% less dense than water, which means it would float right on top.
So think about that. With just a few basic ideas, we can start to translate the messy, chaotic world of fluids into the clean, clear language of numbers. We've gone from just watching something flow to actually understanding why it flows. And that leaves me with one final question for you. Now that you can see these hidden rules at play, what other invisible forces are you going to start noticing shaping the world all around you?